Welcome back. In the last chapter, we have studied what's meant by electric current. Now, in this chapter, we are going to study what is meant by electric. Before going into electric circuits, let us remember the main ideas or the main laws from the electric current. If we have a simple device like a resistor connected to battery by using electric wires like this, there will be electric current flowing from the battery to the resistor and going back to the battery, and the relation between the electric current and the potential difference on the two terminals of the battery is R, the resistance, equals the potential difference over the current. Or in other words, it can be arranged as the electric potential V between the two terminals of the resistor equals the current passing through the resistor multiplied by the resistor. And also we have said that the total dissipated power from the battery equals the value of the electric current multiplied by the potential difference of the battery. And actually, this dissipated power is already dissipated in the resistance as a thermal heat. So if we are talking about the dissipated power in the resistor, we can say that instead of V, we can say I multiplied by R, so it is I squared R. Or instead of I, we can say V over R, so B equal V squared over R. That we have studied in the previous chapter in electric current. Now, we are going to study basic DC circuits. We say that in this chapter we cover the physics of electric circuits that are combination of resistors and batteries, and also there is some capacitors too. We are going to restrict our discussion to circuits through which charges flow in one direction. This means that the current flow would be in one direction only. It will not flow in this direction for a while and then return back. It will always, all the time, flow in one direction. So, flowing in one direction called direct current circuits, or it can be abbreviated as DC circuits. So, our study here is limited only to DC circuits. To make current flow or direct current flow through a resistor, it would be required to have a pump which pumps this charge to flow along the resistor. So if we want to make charge carriers flow through a resistor, we must establish a potential difference between the ends of the device. We have to obtain potential difference between the ends of the device. To produce a steady flow of charge, you need charge pump. Charge pump is a device that is doing work on the charge carrier to maintain the potential difference between the two terminals to be constant. So we will call this battery for a while as a charge pump. So this charge pump pumps the charge to make the current flow through the resistor. And in this case, the potential difference between the two terminals of the resistor would be the current through the resistor multiplied by the value of the resistor. This charge pump is called EMF devices. EMF is from electromotive force devices. Motive M force. Electromotive force devices. So we call such charge pump and EMF devices or electromotive devices. And the device is said to provide EMF, capital E. This is delicate E. So this is the notation of the EMF device in general, which means that it does work on the charge carriers. The term EMF comes from the phrase electromotive force, which was adopted before. Common EMF devices are the battery. The battery actually is the simplest EMF device, which you can see. Another form of EMF device, electric generators. For example, the generator in the car is electromagnetic force device. So effectively in the car we have two types. We have a battery and electric generator. And at the starting, the car depends mainly on the battery. During the car is moving, it depends on the electric generator. Another type of EMF devices is solar cells. Solar cells is another type of electromotive force devices. These devices are completely different from each other on the basic theory of how to introduce this charge pump. For example, battery is based on chemical energy. Electric generator is based on mechanical energy, converting mechanical energy into electrical energy. Solar cells is based on converting solar energy into electric energy. So we say that although the devices we have listed differ widely in their modes of operation, they all perform in the same basic function. They do work on charge carriers and thus maintain potential difference between their terminals. So they are common in one thing, that the two terminals of this device has a constant potential difference. This potential difference may be due to chemical energy or mechanical energy or solar energy, it doesn't matter, but the main common between them is that they have potential difference between their terminals. So in general, if we are talking about electric circuit, we needn't to be talking about a battery. We mainly talking about EMF device. So this can be battery, generator, solar cell, or any other way to generate electromagnetic force. So electromagnetic force source connected to a resistor by using a wire, and actually the wire here are perfectly conducting material, so they are equipotential. Means that the potential of this point is the same as the potential of this point is the same as this point until I reach the resistance. Then there is a voltage drop, as you will see, or voltage difference at the resistance. Then the potential of this point is the same as this point, as the same as this point until I reach to this. Okay? So from the point of view of work, energy, and electromagnetic force, the electromagnetic force device keeps one of its terminals, called the positive terminal, at higher electric potential. So this point is always higher potential than the other terminal, which is called the negative terminal. So assuming that if we are talking about electric potential here, for example, 5 volts, and here 1 volt, so this point is higher than this point. Usually, we say that the negative terminal is 0, for example, and the positive terminal is X volts with respect to the negative term. We can represent the electromagnetic force of the device with an arrow. This arrow represents the electromagnetic force, and this arrow points from the negative terminal towards the positive terminal. So electromagnetic force is represented by an arrow, and this arrow starts from the negative terminal to the positive terminal. And actually, to differentiate between electromagnetic force or the arrow of the electromagnetic force and the arrow of the current, we have added a small circle in the arrow of electromagnetic force. Okay, so this small circle is made to differentiate between this arrow and this arrow. So this arrow represents potential difference. This arrow represents the direction of current. Okay, when an EMF device is not connected to a circuit, for example, a battery not connected to any circuit, the internal chemistry of the device doesn't cause any net flow of charge carrier within. It means that if I have a separate battery, for example, so the positive terminal will have positive charge, accumulated positive charge, and the negative terminal will have accumulated negative charge, and there is no any net electric current or electric charge motion through the device in this case. Now, if I have connect this EMF device to a resistor through wires, so when it is connected to a circuit, its internal chemistry causes a net flow of positive charge carriers from the negative terminal to the positive terminal of the EMF. So once it has been connected, positive charges here from the negative side will flow towards the positive terminal. Positive charge, not negative, positive charge here from the negative terminal will flow towards the positive terminal. Then they will accumulate more and more, so they will pass through the wire, the conducting wire, to the resistor, and then will go from the resistor, will go back to the negative side once again, and this will continue. So once it has been connected, there is positive electric current, and we have said that the motion of positive charge corresponds to the direction of positive electric current. So positive electric current will flow from the negative to the positive, and then this current flow will continue to flow through the resistor and go back to the negative side. So that's what we are seeing. When it is connected to a circuit, its internal chemistry causes a net flow of positive charge carriers from the negative terminal of the EMF to the positive terminal of the EMF in the direction of the EMF arm. This flow is a part of the current that is set up around the circuit in the same direction. At any time interval delta t, for example, the charge delta q passes through any cross section. Assume that we have this cross section area AA dash, for example. So at delta t, delta q passes through it, and delta q over delta t is this current I. So the same amount of a charge must enter the EMF device at its low potential. So the same amount or the same rate at the same time, delta Q at the same delta T will enter the negative side or the negative terminal of the EMF device and leave its higher potential in. And also the same amount delta Q and the same delta T will pass or leave through the positive. Now, if you look at the potential at the EMF, the electric potential is E, and the charge passed through it is delta Q. So, in this case, delta Q multiplied by the electric potential represent the work done on this delta Q charge. Or in other words, the electromagnetic force is delta work, the incremental work done, over delta Q, the incremental charge at this point. So that's what we are saying, the device must do amount of work delta W on the charge delta Q to force it to move in this way. So effectively the rule of the EMF device is to do a work on the charge to move along the circuit. And the value of the electromagnetic force is actually the value of this work over the value of this charge. For the case of an idle EMF device, the EMF device is only composed of charge pump without any resistance inside it. So is one that lacks any internal resistance to the internal movement of a charge. It just pumps the charge without any resistance. Actually, real EMF devices include inside it internal resistance. So a real EMF device, such as an real battery, it has internal resistance to the internal movement of the charge. While you are solving problems, if I didn't mention anything about the internal resistance, this means that take the internal resistance as 0 and you are talking about idle EMF device. But if I have mentioned internal resistance, it means that I want this internal resistance to be taken into consideration, as we will see in solving a problem like this in the following video. See you in the following video. Okay.